Hello everyone, my name is Ankit Pensia and today I will talk about sum of squares proofs and Subgaussian distributions. This is a joint work with Diakonikolas, Sam Hopkins and Stefan Tiegel. Let us start with the motivation and consider this generic estimation problem. We are given samples from a distribution Q which lies in the distribution family script P, and our goal is to estimate the parameter theta star of this distribution Q. Naturally, as we impose more and more structural assumptions on the distribution family P, it is possible to use that additional structure and information to obtain smaller and smaller error. At the same time, we want to ensure that the assumptions are minimal so as to be realistic. However, somewhat surprisingly, computationally efficient algorithms are unable to leverage this additional structure unless the structural nice assumption is itself algorithmically tractable and not just informative. These terms are a bit vague right now, but I will explain what they mean in the next few slides. In today's talk, I will focus on this tension between niceness and tractable niceness for a certain class of problems. Going into a bit more detail, let me first talk about the correct notion of niceness. For many important statistical tasks, it turns out that the optimal error depends only on the tail behavior of the linear projections. Equivalently, the size of the moments of linear projections. Thus, the correct notion of niceness for these problems is the bound on the moments. For example, assuming that the distribution that x comes from is Gaussian is unrealistic, while assuming that the moments of x are less than that of Gaussian is both realistic and sufficient. And this is exactly the class of sub-Gaussian distributions, a widely popular and useful concept in probability, statistics, and computer science. So these are the class of distributions whose moments are upper bounded by those of a Gaussian. Equivalently, a distribution is sub-Gaussian if its tail decay is upper bounded by that of Gaussian. To summarize, we have significantly relaxed the Gaussianity assumption while keeping the same or similar optimal error for many estimation problems of interest. Now, coming back to computational efficiency, existing algorithms are often unable to use this sub-Gaussianity structure and thus incur large error. This is despite the fact that there are plenty of algorithms that work very well for Gaussian data. And this leads to the natural question, if there is a computationally tractable notion of sub-Gaussianity. The challenge is to check if the higher order moment polynomial corresponding to the tth moment is bounded from above. This is equivalent to checking is a certain translation of this polynomial non-negative. However, in general, this is NP hard. However, what we can check is if it is a sum of squares polynomial, which are a strict subset of non-negative polynomials. Indeed, this task is algorithm friendly because it can be done using semi-definite programs. This algorithm friendliness nature of sum of squares polynomial motivates the concept of certifiably Subgaussian distributions, which are a subset of Subgaussian distributions such that the difference of these moments is not only bounded, but also a sum of squares polynomial. To repeat, this condition is highly non-trivial because many non-negative polynomials are not sum of squares. This definition was introduced in these two works and has been hugely influential since then. Indeed, if the data satisfies this stronger certifiable Subgaussian assumption, then we do get polynomial time algorithms for many important problems. This leads to a natural and important question: which distributions are certifiably Subgaussian anyway? We now want to understand which Subgaussian distributions are also certifiably Subgaussian. Unfortunately, our understanding of this question was quite limited. First, if a Subgaussian distribution satisfied additional regularity conditions, such as rotational invariance or independent coordinates or being a sigma Poincare or a log Sobolev distribution, then it was guaranteed to be certifiably Subgaussian as established in prior works. However, these conditions are quite strong. And for each one, we can find a Subgaussian distribution that does not satisfy it. In fact, the certifiability assumption is strictly stronger in general. For example, under the small set expansion hypothesis, there are distributions whose 100 moments are bounded, yet even its fourth moment is not certifiably bounded. Because of results like this, a popular belief in the community was that there is a fundamental gap between Subgaussian and certifiably Subgaussian distributions. In other words, many believed that there exists a Subgaussian distribution that is not certifiably Subgaussian. In contrast, a more optimistic perspective would be that this gap does not exist, and that we do get computationally efficient algorithms without requiring strong assumptions. So with this background, the question we ask is, can we characterize the class of certifiably Subgaussian distributions? And in this work, we settle this question. We show that, contrary to prior held beliefs, every Subgaussian distribution is certifiably so. To be precise, the difference here between the moments can be written as a sum of squares polynomials. This answers many open questions from the field. In contrast, even for the fourth moment, the previous bounds were vacuous and scaled polynomially with the dimension. Beyond this particular algorithm-friendly structure, we show that all Subgaussian data have many additional algorithm-friendly structures that give rise to efficient algorithms. At a conceptual level, we make connections between SDP relaxations and the theory of empirical processes, and I will expand on this proof technique in a couple of slides. Having established that the Subgaussian data do have algorithm-friendly structure, we immediately get new algorithmic guarantees for Subgaussian data. And I will now elaborate on the applications in robust statistics, which was the primary motivation for us. We give the first polynomial time algorithm that is robust to outliers and work for all Subgaussian distributions, solving covariance estimation, linear regression, and so on. In contrast, prior polynomial time algorithms gave vacuous guarantees. Moreover, we also improve error guarantees for other important problems, such as robust mean estimation and clustering. In contrast, previous polynomial time algorithms had much larger error because they were using only the bounded covariance or the bounded second moment information instead of fully leveraging the Subgaussianity structure. Furthermore, all of these algorithmic guarantees that we obtain are qualitatively optimal within restricted families of algorithms because they match existing computational lower bounds. For further applications, please also see Stefan's talk on our companion paper. As an example, here is a table of results that follow from a single structural result. Now let's go through the proof sketch. Surprisingly, the proof consists of only 3 steps, with each step leading to an equivalent formulation. The first step relies on the strong duality for semi-definite programs. To build intuition, let's compare the original Subgaussian formulation on the left with its semi-definite relaxation on the right. Recall that a random variable x is Subgaussian if its moments are bounded in all directions. Here, QV represents the tth moment along the vector V. Now, since this inequality holds for every direction V, it also holds if we take an expectation over any distribution on V. Rearranging, we obtain a new formulation where we maximize over all feasible expectation operators. Importantly, this depends only on the tth moments of the underlying distribution over V. Now, since the set of these moments is convex and the required inequality is linear in the moments, this is a convex program. Still, we cannot check this condition efficiently because this set is too large and intractable to optimize over. However, as we'll soon see, the notion of certifiable subgaussianity makes this set tractable. Now let's consider the corresponding statements for the semi-definite relaxation. Recall that the distribution X is certifiably subgaussian if the moment inequality has a sum of squares proof, which, as we saw earlier, is equivalent to a semi-definite program. By SDP duality, this turns out to be equivalent to a similar formulation on the left, but with one crucial difference. Instead of taking maximum over expectation operators, we now take the maximum over a set of so-called pseudo expectation operators. Although I won't go into the full details here, the pseudo expectation operator here shares many properties of the regular expectations. For now, all we need to know is that they are also linear, just like the expectation. Visually, these pseudo expectations approximate the set of moments from above. The main takeaway is that to show certifiable subgaussianity, we just need to prove that the dual term on the right is bounded. And here is the dual term again. On this slide, we'll perform three very simple transformations. First, we replace the single expectation with an average over multiple IID samples from the distribution X. Since Xi is our IID with X, the expectation is identical. Next, using linearity of both expectation and pseudo expectation, we will swap their orders. And finally, by Jensen's inequality, we'll put the supremum inside the expectation. Now, if we take a step back, this is simply an empirical process over a certain class of functions which come from the set of pseudo expectations. Thus, to prove certifiability, we need to show that this empirical process is bounded for all subgaussian distributions. To understand empirical processes, a foundational result in probability is Talleyrand's generic chaining, which implies that all subgaussian linear processes are upper bounded by Gaussian linear processes. However, our process is defined by nonlinear functions. Indeed, each f here is some polynomial of x. And generic chaining does not give right results even for arbitrary quadratic polynomials. But one still wonders if we could still apply generic chaining. Encouragingly, Talleyrand's result applies not only to linear functions, but also functions that are sufficiently linear. That is, functions that can be expressed as the supremum of linear functions or powers of such suprema. Motivated by this, we show that our function does have this structure. As a consequence, we can apply generic chaining to replace sub-Gaussians with Gaussians. Now we can see the full proof in its entirety. Now we can see the full proof in its entirety. We start with our goal, showing that X is certifiably subgaussian. By duality, this is equivalent to proving that a certain empirical process remains small. We then linearize this process and apply generic chaining to replace sub-Gaussians with Gaussians. Next, we reverse the reasonings for Gaussians, following the same argument as before. Since we already know that Gaussians are certifiably subgaussian, this gives us the final result that every subgaussian is also certifiably subgaussian. I now conclude. We showed that all subgaussian distributions are certifiably subgaussian And we also discussed algorithmic implications of this result. In terms of open problems, a main important direction for future research is to go beyond the class of sub-Gaussian distributions and study what are much weaker classes of distributions, such as sub-exponential distributions, or um, that do have certifiably bounded moments. For example, what are the minimal assumptions that lead to the fourth moment being certifiably bounded? Another important direction here is to develop algorithms that not only run in polynomial time, but also are very practical. For example, does there exist a linear time algorithm with similar accuracy guarantees? Thank you for your attention, and please attend Stefan's talk during the conference. Thank you.